In this example, we are given a single loop circuit, and it's called single loop because it has one loop in here. And in this particular circuit, it has a voltage source and a resistor, and we are asked to compute what the current flowing through that single loop circuit is. And in this particular case, we are given the direction of I, so we are not given the liberty to decide whether is I going that way or I is going this way. We're asked specifically that I is going that way, just compute that value associated with it. And also we are told to compute the power supplied by the voltage source. Obviously we have two elements in this circuit. A resistor cannot generate power, so the only source of power must be the source. So in this particular case, the source is generating power. We know that ahead of time, and we're asked to compute by how much power is it generating. So let's get started, and what I will do is I'll first focus on figure out I, because obviously in order for us to compute the power, we need the voltages and current. And I'm looking at here, and what I have is I. So obviously, since it's a resistor, that means I have to use Ohm's law. So let me just write that. So V equals I times R. And typically throughout circuit analysis, if I'm asked to compute a certain value or measure or a circuit variable associated with an element, you'll see me focusing on that element alone, and that will become obvious. Why will become obvious in a second. So I'm going to focus on this particular resistor. So I know that V equals I times R. I do have the value of R. This is the 2.5 kilo ohms. I is what I'm looking for. V, well, do I have voltage? Well, as it turns out, in this particular circuit, I know that the voltage source in here, I can just say this is plus. It's the same as this plus in here. And I can say that this is minus. It's the same minus in here because there are no elements in here and no elements in here. And this particular voltage source, I will call it Vs, is just simply 40 volts. So as it turns out that yes, I do have the voltage across that particular resistor. So I do have that. Okay, so I have the voltage, I have the R. I can easily just compute what I is. But before I continue, I just want to make sure the passive sign convention has been applied correctly. So based on the direction of the current and the polarity of the voltage, and focusing only on the resistor. Remember, it's like, I focused on the resistor or highlighted the resistor for a reason, because I want to see where the current is hitting the resistor, not the source. So in this particular case, the current is actually going and hitting the negative port first. So what I need to do is I need to put negative in here. Right? If I was focused on the source in here, I would have seen that the current is actually going that way and hitting the positive first, and I would have used the positive. But in this particular case, for Ohm's law, and since I'm just using or focusing on the resistor, I usually look, okay, the current is hitting this particular element, so it's hitting the negative port first for the R. Ohm's law applies to the resistor, not to the source. All right, so moving on, well, I'm looking for I, so all I have to do is just rearrange these terms a little bit, and that becomes negative V divided by R, and obviously we know that V is 40 volts, and we know that R is 2.5, and because it's kilo ohms, I have to move it or convert it to ohms, and you will see that the answer is negative 16 times 10 to the negative 3, and that's amps, or simply 16, or negative 60 milliamps, okay? And just a quick comment in here, if you see that the voltage is actually in volts and the resistor is in kilo ohms, typically you can directly just compute them, and the answer will be in milliamp for the resistors without having to go multiply by 10 to the power 3 and then 10 to the negative 3 in here. Anyway, so we found out that the value of that current is negative 16. So what does this negative imply? Well, the negative implies that the direction of the current, the actual direction of the current, is opposite to this assumption. The current is actually flowing out of the source, going to the resistor, and coming back to the source. But because we assumed or we wanted to compute the current flowing this way, we got the negative. So the negative just tells us that this assumption is just mistaken and wrong. However, we will not change this assumption, and whenever we want to use the I, we just substitute it with negative 60 milliamp, and that's about it. Okay, so moving on, let's compute the power. So there are multiple ways to compute the power. Obviously, because we have two different sources, we can either compute the power consumed by R, and we say, well, if the power consumed by R since I only have two elements, the sum should be 0, so the power consumed by R should be the same as the one generated by the voltage source. But I'll just, instead of that, I can just, well, actually, let me just solve that. So the power associated with R is simply, we know that it's either I squared R or simply V squared divided by R. Either way is fine. So I will take a look at the I squared R. So it's negative 16 times 10 to the negative 3 because it's a milliamp squared times 2 to the power 2.5 times 10 to the power 3, and we'll figure out that in that particular case I don't have passive sign convention for this particular rule, because I know that v squared is a positive and r squared is positive, or I squared is positive and r is positive. I know that the P of the resistor has to be positive because it's consuming power. So it's not the power generated, it's the power consumed by this particular resistor. So let's compute that value, and that value will be 0.64 watts. There's another way we can compute it using the resistor. So let me just do that here. So P times R is typically I times V. That's the definition of power. And again, because we're focusing on the resistor, because we're computing the power for the resistor, so I have to focus on the current and voltage relationship for that particular element, the one that is highlighted. So I have the current going in here. It's hitting the negative first. So that means that I have to use the negative in here. All right, we substitute specific values. We have negative, and the current value is actually -1 or -16 times 10 to the -3, and then we'll multiply it by 40 volts. That's what we do. And if you basically compute the value, you should see that we have the same exact answer, which is 0.64 watts. So the power consumed by this resistor is 0.64. But this isn't what we're asked. We're asked to compute the power supplied by the voltage source. Well, one way to do that is by telling me, well, the power for the source plus the power for the resistor should be equal to 0. That means the power of the source is simply the negative of the power of the resistor, which is negative 0.64. So that's another way to compute it. Well, okay, or this is how we computed the power for the source. But what if I want to directly compute the power associated with this source using P equals IV? Well, in this particular case, I have to focus on this element now. Okay, just this particular one in green. All right, so let's compute that one here. Okay, and I'll just basically compute it in red. So the power of the source, according to power definition, is I times V. However, I need to make sure that the passive sign convention applies in here. So current is actually flowing in here, it's flowing in here. Again, I'm computing the power that is highlighted in green for the source. So in this particular case, the current is hitting the positive first. So I have to use positive in here. Okay, we substitute the values. The value is -16 times 10 to the -3 times 40 volts, which is 0.64. And this time it's actually in the negative because it's actually generating power. It's a negative power. And we got the same answer we got in here. So that source is providing -0.64 watts.